introduction, and I would like to thank the organizers. It's a great honor for me to start as a keynote speaker the Transnational Access Session. It's a very splendid infrastructure that is built there with huge potential. And I would like to introduce you to the results of a recent FP7 project that I had the honor to participate in. It was called Chronometer, the coordination of nanometrology in Europe. And I would like to acknowledge my co-authors who helped in assembling the results that I will talk about today. And here you can see the whole consortium spread out over whole of Europe that actually actively participated in the coordination of nanometrology. This is a short overview of my talk. I would like to introduce the concepts, the principal concepts of metrology. What is it? What is so special about the science of measurement? Then we have heard about challenges in nanotechnology. I would like to transfer these challenges to nanometrology. Why is it so difficult to measure small structures? Then I will come, after the technical discussion, I will come to a mapping of European facilities and capabilities regarding nanometrology. I will come with the actual key point of my talk, with a proposition as a recommendation for the infrastructure requirements that we need in Europe and strategies. And I would like to sum up then with the outcome of our project and point out current opportunities. Now, metrology, the science of measurement, was actually one of the first sciences that were developed by humans when we stopped hunting. When we became settlers, it was important to know the size and the area of our farming fields. And the first thing you need to do is, how do you want to express the thing that you want to measure? Now, up to the French Revolution, usually some body part of the ruler was involved. In the Egyptian times, it was the arm length of the pharaoh. It moved then from the belly circumference of the chief to the distance between the tip of the nose and the extended thumb of the king. But at some point at the French Revolution, if you allow the picturesque comparison, when they were busy getting rid of the king's head, they might as well get rid of the king's foot. So the 1 meter was defined. And the 1 meter was in those days defined as the 10 millionth part of the distance between the North Pole and the equator. Now, it took 7 years for the scientists back then to establish this measure, so I cannot really sum it up in 7 seconds, but you are free to ask me later. So now we know what or how we want to express the length. The next thing is, now we have the theory, now we have to make a realization of the unit. Well, using, let's say, a granite copy of the pharaoh's arm length, we already had the possibility of a standard. From the meter, originally a platinum bar was fabricated with 2 lines indicating the distance of 1 meter. Today, we are using a laser setup where we actually refer to the constant of nature, the speed of light, that gives us a much more accurate realization of the meter. Once we have the units, the next thing which is utmost important is the measurement uncertainty. You know that material elongates when you heat it up. Platinum has an extension coefficient of 10 micrometer per degree centigrade. So with the platinum bar of 1 meter, we could not do any nanometrology unless we could stabilize the temperature within 1 millikelvin. That was really critical, and even if you think that, well, constant of nature, nothing can go wrong there, well, the speed of light is defined in vacuum, but we are measuring in air. So we need to take the measurement uncertainty into account that is imposed into the measurement by measuring in air. Next to this, now we have established the standard, the measurement standard. Now we can calibrate further measuring instruments, a micrometer screw, a caliber, a scale. And by calibrating, by comparing the readout of the instrument with our standard, we establish the so-called traceability. The unit can be traced back in this chain. Next, if a significant amount of people agree to perform measurements in this way and adhere to the same way of determining uncertainty, then we can sign a mutual recognition agreement, and we can agree that those that have signed the treaty measure correctly, and we don't need to certify or test, verify their measurement results. That leads to standardization, and today we are in the privileged position that we can buy a bolt in, let's say, Moscow, and we can buy a nut, let's say, in Madrid, and you can screw them together and they fit. 200 years ago, this was not possible. Finally, then we have built the foundation to develop industrial and legal metrology. In 1875, the Convention of the Meter created the International Bureau of Weights and Measures in Paris, which ensures the worldwide uniformity of the measurements. Now there are 45 member states. The mutual recognition agreement has recently been signed again, and there are more than 230 institutes that adhere to these standards to perform the measurements related to the Meter Convention. Regional metrology organizations, RMOs, they locally assist in distributing the measurement knowledge. In Europe, that is Euramet, the Association of National Metrology Institutes. And in order to assess that the measurements are still valid, key comparisons are performed to test the principal measurement techniques in the metrologic field. And first, when these so-called calibration measurement capabilities are registered in the database at BIPM, then we can be sure that the measurement is performed according to the rules. Moving to Chronometer now, we focused on 5 different areas related to nanometrology, nanotechnology, engineered nanoparticles, nanobiotechnology, functionalized surfaces, thin films, but also dimensional measurements, and modeling and simulation was one of the issues that we focused upon. Yesterday, during the speeches, and also yesterday evening in the talk, I had some interesting remarks, and I would like to focus a little bit more on the difficulty of measuring particle sizes. Here are a lot of different measurement methods, ultrasonic measurement methods, optical measurement methods, gravitational measurement methods, image analysis methods that can assess a particle size. But still, you need to take a look at what kind of media is it that you are measuring the particles in. Particles can have a very broad measurement range. So if you have a bimodal distribution with very small particles and very large particles, it might not be, your choice of measurement method might not be the most appropriate. Are the particles singular, or are they in an agglomeration state? But above all, these measurement methods, as soon as you pass the critical level of 100 nanometers, they behave differently. They sense the particle in a different way. This is a study of the American Metrological Institute, NIST, where they used their own reference material of gold particles and analyzed their reference material, the same particles with different measurement methods. And you can see that as long as you are, about 80 nanometers, everything behaves nicely. When you are then going to smaller particle sizes, you can see that the size distributions of the different measurement methods, they are starting to drift apart. And as soon as you are down at nominal particle sizes around 10 nanometers, then the size distributions and the mean values of those, they are completely different. Putting this into some diagram, you can now here see the different measurement methods. being operated on the same particle material. The error bars here are not the statistical spread of the measurements, but they represent the actual measurement uncertainty as assessed by the Metrological Institute. So this would mean that if we measure again, then we can say with 95% probability that the new measurement will yield a mean value within this interval. So we cannot measure better as than plus minus 1 nanometer with a 95% probability. We have recently, in another European metrology project, repeated this exercise with different participants with a different type of reference material, but still you see the same systematic effect that the AFM tries to or finds a diameter value for the particle that is smaller than electron microscopy measurements or electrical mobility measurements with the SMPS. And the reason behind it is, here I have imaged with the AFM a calibration soot particle with a nominal value of 70 nanometers. It might be large to your scale. You can nicely see that this soot particle has an internal structure of primary particles, and I was lucky to find one of these 30 nanometer primary particles isolated on the substrate. So the question is, which one quantitative value would you associate with this particle that represents its size? Is it the 40 nanometer height, because the particle obviously has flattened out on the substrate? Or is it the largest distance? Well, I settled for the volumetric equivalent diameter, where I integrated over the whole particle material and calculated the volume of an equivalent sphere that would, the diameter of an equivalent sphere that would produce the same volume. And the 76 nanometers is not too unrealistic for this guess. Now, light scattering, you might feel yourself on the safe side. It's a first principle method. You have the Maxwell equations. You cannot argue with them. Me scattering theory tells you how to solve the Maxwell equations. You have a mathematical exact process. So you should be on the safe side. But there is one parameter that enters the equation, and that is the refractive index of the particle. Admittedly, these are calcium carbonate particles at the micrometer range. But as you can see, if I recalculate the measurement result with a varying refractive particle index, you can literally generate any particle size distribution that you want. So we also need to take care of the surrounding parameters that enter the measurement method. Going back to infrastructures now from the technical part, there has been a European survey, where an online survey where you could report your opinion in, and it can be seen that a lot of effort has to be or is demanded with regard to communication and public dialogue, but there's also the part of development of an infrastructure that is emphasized in this survey. So Chronometer took up the task and made an inventorization of all, well, not all, those we could contact, nanotechnological measurement devices in Europe. You can find this on this website, and you can click on a country, for example, the Czech Republic, and you get a nice overview of the different measurement methods that are available here. Now, the outcome of this survey was that 20 out of 34 NMIs have no visible nanometrological capacity. That 5 countries, they own more than 50% of the total facilities. Good thing is, more than 75 of the facilities are within the public sector. The university-based instrumentation are the largest contributor to this infrastructure. The Academy of Sciences in Bulgaria, also in the Czech Republic, they play a significant role in giving access to these measurement instrumentations. Some countries, they have created a regional governmental research infrastructure. And what's most puzzling is, on a worldwide basis, only very few NMIs they offer traceable calibrations under the meter convention in the field of nanometrology. So this is where we have to do more work. Our requirements, as we saw it, as we see it, for future infrastructures in nanometrology is this triangle. We need instrumental hubs. We need people that put their instruments into projects, like the Transnational Access is a perfect example, so that we, the National Metrological Institutes, don't have to buy expensive instrumentations. The smaller the things are that you want to measure, the bigger the instruments get and the more expensive. The next thing is there where we put metrology into this infrastructure by use of centers of excellence, stakeholders from the industry, guidance from national metrology institutes and universities. They have to ensure that and sustain the techniques that are developed there. And finally, to live up to the call of dialogue and transparency, there are centers of disseminations that really make the results public and also lead to standardization development so that the results really are on safe grounds. This is the recommended structure. Down here you can see the three parts from the previous triangle, governed by topical committees. This could be particle size, surface area, surface charge. Then the regional metrology organization, for example, Euromet, would be a perfect partner to lead the infrastructure management, develop a roadmap, what needs to be done, distribution of the projects to the partners. And there should also be an advisory board that is the contact point for stakeholders and that also distribute the access to the databases and to the instrumentation. With this, we hope to give a structure that allows a large scale and as well as singular facilities. It should be funded not by a single state, but by member states in order to give possibility for international exchange. We should create rich environments because we want to attract and keep foreign researchers. The multidisciplinary training helps us tackle the grand challenges. The openness allows peer-reviewed access to the infrastructures. And finally, the development of industrial-oriented research facility can also be promoted by attracting more contributors, partners from the private sector. And with this, I would like to come to the final slide. The outcome of Chronometer has something happened. Yes, indeed. In the latest call of FP7, there were actually two topics, 142 and 143, that explicitly now state the need for metrology in the development and validation of nanostructured materials, and also the need for standards and standardization supporting the recommendation of nanomaterials. Literally, an indicator of the project's potential will be the involvement of metrology institutes and or standardization bodies. So with this, I would like to kindly ask you, please, during your next project application, consider the participation of your local National Metrology Institute. I thank you for your attention, and I'm ready for your questions. Thank you.
Okay, we have time for one or two questions. Other questions in the audience?
Is there anything like, well, first of all, thanks for the good oversight and the work done, wonderful. But is there like a common agenda by the metrologists, institutes in Europe, that they see this as a problem they want to tackle? Or is it a matter of funding and again, everybody on its own again?
One of the slides, I very briefly mentioned the European Metrology Research Project. This is a program that has been going on for the past 4 or 5 years, where limited to the participations of national metrology institutes with a few stakeholders that of course support the research. We have gotten the task to develop new metrology. So the European Commission is well aware of the need for it, and we are doing our job as good as possible. But again, this is us, and this is you, and we need to bridge the gap somehow. So we really need to make some interdisciplinary effort. Yeah.
Okay, more questions? Okay, then thank you again, Kai, and we are ready for the next talk.